All right, let's talk about power. Not just any power, but the kind of raw, immense force that's trapped miles under our feet, just waiting to get out. It all boils down to one really, really important question, right? How do you possibly handle that kind of insane pressure without everything going sideways, catastrophically? Well, the answer is a pretty incredible masterpiece of engineering, one that's designed to tame an absolute monster. Let's break down exactly how it works.
So, to get our heads around this thing, I want you to think of it as the most robust, high-stakes faucet ever built. Seriously, it is the one and only control point between the raw power of the well and, well, everything else on the surface. At its core, the choke manifold is really just an assembly of super heavy-duty valves and some specialized things called chokes. Its entire reason for existing is to precisely manage the flow and the pressure that's coming out of the ground. Doesn't matter if you're drilling a new well or just managing one that's been around for a while. Now, to really put this into perspective, think about the faucet in your kitchen. It's handling water at maybe 50 psi. A choke manifold, on the other hand, is engineered to control a blistering hot mix of oil, gas, and abrasive sand at pressures that can hit 20,000 psi. That is 400 times the pressure, with sand literally trying to blast its way through the steel. It's not just a different league, it's a completely different sport. Okay, so you have this absolutely critical piece of equipment. How in the world do you make sure it's ready for that kind of abuse? Well, it all starts way before it ever gets near the well site, with a checklist that is just meticulous. Honestly, you can think of it like the pre-flight check for a rocket launch. I mean, every single detail gets scrutinized. You're looking for any little sign of damage. Every port gets plugged up so no junk can get inside. And here's a really crucial detail. The valves are transported in the open position. Now, why would they do that? Well, it protects the most delicate parts, the sealing surfaces, from getting banged up during the trip. It's all about stopping a failure before the job even starts. This gets right to the heart of the whole safety philosophy. It's completely non-negotiable, and for a very good reason. Under thousands and thousands of pounds of pressure, a tip that's just screwed on could shear right off and become a projectile. We're talking a metal bullet fired out of the system. So by making sure it's an integral one-piece design, engineers just completely eliminate that risk.
All right, so the manifold arrives on site. You don't just, drop it into place. The physical installation, what they call the rig-up, is a science all by itself, where the entire layout is engineered for maximum safety and, of course, performance.
And every rule here is critical. You want shorter, high-pressure lines because it means less risk. Grounding it electrically, that prevents static buildup and sparks. A clear escape route, yeah, that's just common sense. But this last one is fascinating, that 1 meter of straight pipe. This little detail lets the super turbulent, erosive flow coming out of the choke just calm down a bit, which drastically cuts down on the wear and tear on whatever component is next in line.
And before a single drop of anything flows, this final step is absolutely mandatory. You physically close the choke until the stem hits the seat, and then you set the indicator to 0. This calibrates the whole system. It makes sure that when the operator's dial says the choke is 10% open, it is actually 10% open. Without this baseline, you're just guessing. You're flying blind.
So, with everything set, it's go time. It's time for the manifold to do its job, to stare down the raw power of the well and bring it under control. And this is where discipline and procedure are absolutely everything.
The first rule is absolute. You never flow against a closed choke. It's like pointing a firefighter's hose at a brick wall and then turning it on full blast. The pressure would just spike instantly, and it could overwhelm the entire system. You always establish a flow path first. This next rule is all about preventing erosion. Running in what they call a pinch-down mode, so less than 20% open, creates this incredibly high-velocity jet of fluid and sand. It basically becomes an internal sandblaster, just eating away at the choke's components from the inside out and causing it to fail way too early. And finally, you have to remember that the manifold is just one piece of a much larger puzzle. Its job is to step that massive pressure down safely so the equipment that comes after it, things like separators and tanks that have a much lower pressure rating, don't get damaged or, completely destroyed.
Now, for stable, long-term production, operators will often switch over to a fixed-size nozzle called a bean. But you can't just shut the whole well down to swap it out. So the procedure is this carefully choreographed dance, and it's all done while the well is live. First, the flow gets diverted. Then the line you're working on is isolated, and that trapped pressure is safely bled off. Only then can you replace the bean. After that, you repressurize the line and divert the flow right back. It's a total masterclass in high-pressure maintenance.
And get this for intensity. If the well is producing sand, those erosive forces are so powerful that crews have to come out with ultrasonic equipment and check the steel thickness of the manifold and all the piping every 2 hours. They are literally watching the equipment wear away in real time, all to prevent a breach.
You know, a choke manifold isn't built to last forever. It has a finite, engineered lifespan that's governed by a really rigorous maintenance and inspection schedule. Kind of like your car, but with far, far higher stakes.
This maintenance schedule is tiered, and it is relentless. At Service Level 1, after every single job, it gets a visual check, a function test, and a pressure test. Then, every year, at SL2, it gets a more detailed survey, including those wall thickness checks. And every 5 years at SL3, it's the big one, a major recertification, where it's stripped down, inspected with special methods, and pressure tested to 1.5 times its normal working pressure.
This timeline really visualizes that entire journey. It's just a relentless cycle of work, inspection, and recertification. And every single step is documented, which creates a complete service history that proves its integrity over those 2 decades. And after 20 years, that's it. It's over. It doesn't matter how good it looks. Its service life is done. The stress and fatigue that have built up from countless pressure cycles mean it has to be retired. It's a hard and fast rule that's all about putting safety above absolutely everything else. So at the end of the day, the choke manifold is so much more than just a piece of steel. It really represents a whole philosophy. Its entire life cycle, from those meticulous checks before a job to the day it's finally retired, is a story of total discipline in the face of just incredible power.
And that leaves us with a final thought, doesn't it? We've just gone through the exhaustive, rigorous life of a single component. It kind of makes you wonder, what incredible level of complexity and coordination does it take to safely manage the thousands of other components that make up the entire system?